Hello, and thank you for coming to Sig School Scholars. Today we'll be continuing to look at uniform circular motion. For the last time we defined it, we derived a formula for a centripetal acceleration, where we said its magnitude was equal to v squared over r, and its direction was always along the radius towards the center. Force, radial force, or we could also call it centripetal force. Same thing towards the center, but its magnitude is going to be m times ar, because force is defined as ma. So we have mv squared over r as its magnitude. Okay, so let's look at solving some problems. First one we're going to look at is we have some object in it is a horizontal circle. We have radius 1.10 meters, so the object is has some velocity moving in this circular path 1.10 meters from the center of the path, and has velocity of 1.25 meters per second, and the object also has a mass of 25.0 kilograms. So the first part is going to ask us to find the centripetal acceleration, which we know will be v squared over r. Second part asks us to find centripetal force, which we know is going to be mv squared over r. So we would just plug these numbers in. We get for the centripetal acceleration 1.25 squared divided by 1.10, 1.42 meters per second squared, and we're going to need to specify direction, because it is in fact a vector. Direction again is going to be towards the center. Now we're going to multiply that by 10. I don't like 25. Let's make it 10, just so we don't have to put back calculator. 14.2 newtons towards the center. Okay, so that's simple enough. Horizontal circle. Vertical circle, will be a little bit more challenging, because we'll not only have a centripetal force, we won't only have if there's a cord attached to the object and attaching it to maybe a person who's holding the cord and spinning the object around. We'll have not just tension there, we'll also have a force of gravity. If we have maybe a a Ferris wheel or whatever, we may have more than gravity. So this is now a vertical circle. So at any time, at the top, the object's Newton diagram will look like this: mg plus ft, and we'll name this one ft1. And at the bottom, the force diagram will look like this. Something like that. Okay, so this is A, and this will be BB. So, what we're gonna say for let's make this one interesting. We have let's say we have a bucket, and that bucket has some water in it. We don't want any water to fall out, and we're swinging in a circle. So we know that the water's not going to fall out if the water and the bucket are given enough of a velocity for the force applied to them, so that the force is just enough, or is sufficient to keep the object moving in a path, to alter its velocity fast enough so that it follows a curved path, but does not cause the contents to spill out, because the object is going to be traveling fast enough. So that's why, if you spin a bucket, the inertia of the bucket and water inside make it so that the water doesn't fall out, as long as it's moving fast enough. If it were to stop moving while it was overhead, of course, gravity would take over and it would just fall out. So, let's say there's a bucket of mass, I'm saying 8 kilograms. Okay, and the person's arm, I guess, is 1 meter. Probably a little bit long, but not really important. Let's write we're trying to, find, let's find the tension at the top and the tension at the bottom. How about we do it this way? We'll say that let's find velocity at top, velocity at bottom, if VB for bottom is equal to 2 times VA, A for top. And this is minimum. Yeah, okay. We're looking for a minimum velocity. The minimum velocity amount of velocity that's required to get over the top, so that it just barely goes over. So at A, sum of forces will have mg plus ft1, of course, equal mv squared over r. Now, as you can see from this relationship, the greater the force, because the mass and the radius are staying constant, the greater the velocity. If we're looking for the minimum velocity, we're looking for the minimum amount of force. Since gravity is not going to change, we're looking for the velocity that's required to get the object over, the bucket over the top, if the tension is 0. So basically, right as whatever the arm, I guess, is going slack. So usually we'd say cord, but since we're using an arm, person's arm swinging it. Well, yeah. So we solve for velocity then. When we get velocity equals the square root of gr, which is just going to be the square root of g because r is 1. And the square root of g is 3.13. So velocity A equals 3.13 meters per second. So that's the first part. Now we need the velocity at bottom. Velocity at bottom is 2. Velocity at top. So it's just going to be 6.27 or 6, yeah. 6.26 meters per second. Let's see. Okay, now let's see what must the force of tension be at the bottom. So at the bottom, the force of tension and gravity are going to be acting opposite each other. So if ft2 minus mg will equal mv squared over r. And this will be m times, if we write this in terms of our v at top, we'll have, this is vb, of course, Remember, VB is 2VA. So we'll have, if we square that, we'll have 4MVA squared divided by R. Which means that FT2 equals mg plus mv squared over R. And that's VB. So, we add those. We get, let's see, mass was what, 8? Yeah. 8 times 9.80 plus 8 times, we're talking about VB again, 6.26 times 6.26 divided by, 1, that's right. So, what we get is like a lot of newtons. Yeah, a lot of newtons. Okay, and again, that's towards center. And so, there we go. So, remember, this the only way we can solve that is if we know that, well, we're looking for the minimum velocity that's required to get over the top. And we're looking for the minimum velocity to get over the top, then we're looking for when the force is minimum, which is, of course, when the tension at the top is 0, and the only force is supplied by gravity. And this is for a vertical circle, of course. So, let's go ahead and erase this. So, what should we... We should do another horizontal circle. So, in this case, let's say we have to make this one a little bit more involved. So we have a mass of 254 grams, revolved in a horizontal circle of radius 3.2 meters. 3.20 meters. And its period is, let's say it this way. It completes 4 revolutions every 3 seconds. Whoops. 4 revolutions per 3 seconds. So, let's go ahead and find... Let's erase this. That's not necessary. Let's go ahead and find centripetal force and centripetal acceleration. So first, we need to find the velocity. We have the radius, we need to find the velocity. And we can find the velocity from this. 4 revolutions per 3 seconds. Well, that means that that is equivalent to saying 1.33, well, it's 1.3 repeating, or 4/3 revolutions per second by just dividing by 3. So, for 4/3 revolutions per 1 second. So, that is a frequency. We need a speed. So, what we're going to do with that is use the reciprocal relationship between frequency and time. So if there's 4/3 revolutions per second, then 3/4 seconds per revolution. Now, we know velocity is equal to 2 pi r over period. So, we use that period, and we take 2 times pi times r, we plug those in. 2 times pi times 3.20 times 4 divided by 3. And what we get is velocity of 26.8 meters per second. And this is tangent to path, as of course that is a vector quantity. Let's say that these are exact, so they have an infinite number of significant, an infinite number of significant figures. So we get our significant figures from the 3.20. Okay, so with that, we can find the centripetal acceleration, v squared over r, and then the radial force of mv squared over r. No real need to carry that any further. Now, okay, so now we've talked about horizontal and vertical circles. We should look at the banking of curves. So, when we look at banking of curves in the next video, we'll start with the knowledge that first we'll look at unbanked curves. So an unbanked curve means that a car is rounding a curve where the road is not angled. So basically the car is following circular motion, following a curved path. And the radial force will be supplied by friction in that case. Okay, thanks for watching the video. Want us to make a video on a specific topic, just leave a comment. We will fulfill your request as soon as possible. You can leave a comment either in the section below or on our website at sigschooltours.wordpress.com. We'll try to fulfill your request as soon as possible. Thanks.